In the next part of the lecture, I'm going to talk about alternating series. So what is an alternating series? An alternating series is a series whose terms are just uh, alternating between positive and negative. Now, the alternating series test tells you the following. So if you have a series whose terms are alternating between positive and negative, so which we know from this -1 to the power n minus 1. So basically, an alternating series is anything that has -1 to the power n or -1 to the power n minus 1, depending on where it starts from. And then if you look at what it is multiplied by, so then let's say it is going to be bn. So the sequence bn is supposed to have a zero limit, and it is supposed to be non-increasing, or, well, decreasing, well, not strictly decreasing. Then the series converges. So notice that it says for all n here, but actually it doesn't have to be for all n. So instead, I mean, it's just like a common sense. So convergence of a series is a condition on the limit, right? So it has to do with the behavior of the series at infinity. So any finite piece of our series does not affect convergence, because again, so convergence is something that happens at infinity. So which really means that if our sequence is non-decreasing, eventually after some n, so which means that if n is bigger than some, or bigger than or equal than some fixed n and 0, then it is okay, it's still going to work. So another thing about this alternating series test is that it only works one way, right? So if these conditions are satisfied, so if our series is alternating, if its terms have zero limit, and if you remove the alternating signs, then whatever remains is going to be a non-increasing sequence, then it converges. But if these conditions are not satisfied, then basically we don't know, so it cannot be applied. So it only works one way. Now, the alternating series test is it's kind of it has a very nice proof too, and I am going to go through the proof of the alternating series test. So if you are not interested, so you can just scroll forward. It is a kind of a little bit harder and longer and more difficult to prove than say the limit test for um, divergence, but still it is a nice proof. So the key to prove it is to try some specific alternating series and to plot its partial sums. And if you do this, you will see that partial sums, even numbered partial sums, increase, while odd numbered partial sums decrease, right? So here they increase, and these are decreasing. And we can apply the monotone convergence theorem here. So we can prove that these two sequences are convergent by applying the monotone convergence theorem that tells you that if a sequence is increasing or decreasing, and if it is bounded, then it is convergent. It has a limit, right? So, and here is how we can do it. So let me write down my alternating series. So as b1 minus b2 plus b3 minus b4 plus b5 minus b6 plus b7, and so on. So recall that the limit of these bn's is 0, and these bn's, they decrease. So all of them are positive, and they decrease. So let me look at even partial sums first. So even partial sums, this is S2, this is S4, this is S6. Well, at the same time, notice that since the all the Bn decrease, it means that B1 minus B2 is, if you just look at this, so B1 is bigger than B2, right? So when we subtract B2 from B1, we get a positive number. So this is positive. Well, non-negative. Same thing here. So b3 minus b4 is going to be non-negative. b5 minus b6 is going to be non-negative, and so on. All right. So every next um, s with an even index is obtained from the previous s with an even index by adding more and more positive terms. But then it means that they increase, right? So the sequence of S2, S4, S6, and so on is increasing. Right? So if you write the sequence S2, S4, S6, S8, and so on. So generally speaking, you can write it as S2N. So this sequence is increasing. Okay, so one condition of the monotone convergence theorem is satisfied. How about the other two? Is the sequence bounded? So can we? Is it true that um, all these s's they are smaller than something? And in fact, it is true. So notice that S2 is. I mean, we can look at it from some kind of slightly different point of view. Look at S2. S2 is smaller than B1, right? Well, less than or equal than B1, because S2 is obtained from B1 by subtracting something positive. How about S4? So now let us look at S4, and here is what we can do. So if we look at this term, minus B2 plus B3, it is negative, right? Because B2 is bigger than B3, so we are subtracting a bigger number than the number that we are adding. So this is negative, and this number is also negative. Right, so S4 is obtained from B1 by adding a few negative terms, so which means that S4 is really less than or equal than B1. But then we can basically go on, right? So if you want to look at the next one, at B6 again, so we added a few negative terms to B1, and then we got S6. B1, and so on, right? So we see that S2 and all of them, for any value of n, they're less than or equal than B1 because they are obtained from B1 by adding some negative terms. So the sequence S2, S4, S6, and so on, as well, the sequence of even partial sums is increasing and bounded, so which means that it must have a limit. So by the monotone convergence theorem, it converges to some limit. So the limit of the sequence S2n as n goes to infinity is some number. Let's say, let me denote that number by say L. Okay, so we have established that. So now let us look at odd odd partial sums. So this was about even partial sums. How about odd partial sums? Actually, by a very similar logic, if we look at these are our odd partial sums. So B1 is just S1. This is S3. This is S5. Well, this is S7. Now, in order to obtain S3 from S1, we subtract B2 and add B3, right? So we include this term, but this term we have just seen it is really non-positive. Again, this term is non-positive. This term is non-positive, and so on. So every next odd partial sum is obtained from the previous one by uh, adding a non-positive number, so which makes it smaller, right? So which means that the sequence of odd partial sums is decreasing. So the sequence of S3 is smaller than S1, S5 is even smaller than S3, S7 is even smaller than S5, and so on, right? So the sequence S2 and minus 1, the sequence of odd partial sums is going to be a decreasing sequence. So is it true that it is bounded? So is it true that s2n minus 1 is bigger than or equal than some number? Well, so what is it bigger than? So let me um, let's think about them. So let us kind of change it around a little bit, and here is what I can do. Um, S1 is just B1 and it is positive, right? So S1 is, well, non-negative. Now, if you look at S3, then S3 looks like this. It is going to be B1 minus B2, which is positive, sorry, plus B3. So this is positive, and this is also positive. So S3 is still positive. How about S5? Now, if you change this, this is B3. So if you change this, if you group B3 with B4, then this is, well, non-negative rather than strictly positive. And there is also B5, which is still non-negative, right? So S5 is the sum of three non-negative numbers, which means it is still non-negative, and so on, right? So basically, you can continue in the same fashion, and by doing that, you will see that all odd partial sums are non-negative. Well, the important thing is that they are bounded from below. So the sequence is decreasing and is bounded from below, which means by the monotone convergence theorem is that it has a limit. So the limit of the sequence of odd partial sums as n goes to infinity is some number which, strictly speaking, could be different from L. We don't know yet, right? So I'm going to write M here. So the last remaining thing to check to make sure that the limit of the sequence of all partial sums, including even and odd, exists, is to check that L equals M, right? So how can we do that? So to do that, we can do the following thing. So what if we take the limit of a sequence, what if we take the limit of S2n minus S2n minus 1 as n goes to infinity, right? So this is going to be L minus M. On the other hand, if you take the even partial sum minus the odd partial sum, what are you going to get? So basically, let me show it here, right? So if you take an even partial sum, like something like, I don't know, like this, minus the corresponding odd partial sum, which is just the previous one, the difference is just minus b, well, in this case is b6, but generally speaking is going to be minus b2n, right? So this is going to be the limit as n goes to infinity of minus b2n. But we are given that this is 0, so our sequence has a 0 limit. So this is 0. So look what we found. So L minus M is 0, so L equals M. So which means that the sequence of even partial sums and the sequence of odd partial sums have the same limit, which therefore means that it is just the sequence of all partial sums has the same limit, and our series converges. It's pretty neat, so which is why I really wanted to share it with you. So anyway, so here is the uh, typed version of the proof. Um, so let me now just show you how we can apply this theorem to conclude that a certain series converges. Right, so the series here is 1 minus 1 half plus 1 third minus 1 fourth plus 1/5, and so on. So it is very similar to the alternating series, but to the harmonic series only we introduce -1 to the power n minus 1. So, and then it kind of changes everything. So remember that the harmonic series itself diverges, but once we introduce plus minus signs, it becomes it starts to converge. Right. So in this case, what do we have here? So we have this is -1 to the n minus 1. So this is our Bn. This is our Bn. And the sequence 1/nth, its limit is 0, right? We know that. And on the other hand, the sequence 1 over n is strictly decreasing. So its limit is 0 and the sequence is decreasing. So it means that by the alternating series test, this series converges. Okay, so basically this is the same thing. And we conclude that the alternating harmonic series converges. So notice that, again, so let me emphasize that if our sequence is, say, non-increasing, or if we do not have -1 to the n minus 1, but something else instead, then it just means that we cannot apply the alternating series test. So, but if we can apply it, then the conclusion is that our series converges. So here is another example. So, and again, so what we need to do is we need to kind of look at the series without the -1 to the power n part, and we denote the remaining part with by bn. So bn is n over n squared plus 1. And we need to verify two things, right? So we kind of, to prove that the series converges, we need to check two things. So one is that the limit is 0. So the limit of bn as n goes to infinity. So we have the limit as n goes to infinity, n over n squared plus 1. And the method to do it, I hope you still remember, is we choose the largest power in the numerator and denominator and divide both numerator and denominator by the largest power. In this case, the largest power is 2, so we divide both numerator by n squared and denominator by n squared. And this is going to be the limit as n goes to infinity of 1 over n in the numerator and 1 plus 1 over n squared in the denominator, and this is 0 over 1 plus 0, which is 0. Check. So the first assumption of the alternating series test is true. So let me make a check here. So the second assumption is to verify that this sequence is decreasing. So is it true that the sequence is decreasing? So that the sequence Bn, so n over n squared plus 1, is decreasing. Well, I think we could plot the graph of this to see if it really works, and it actually works. But maybe the most straightforward method to do it is to use a fitting function to write f of x, basically to replace n with x and to differentiate and check that the derivative is negative. So f of x is x over x squared plus 1. We can check that f prime of x is negative. Is it true? And actually it is true. Yeah, so f prime of x is going to be just, this is the ratio, so I can apply the ratio rule. So x squared plus 1 squared in the denominator. In the numerator I have fg prime, f prime g minus fg prime. So x squared plus 1 minus x times 2x, so which is 1 minus x squared over x squared plus 1 squared. The denominator is just positive, so in order to figure out whether it is positive or negative, we'll look at the numerator, and the numerator is negative once x is bigger than 1. So this is negative if x is bigger than 1. So remember that we are not really interested in all values of x, we are only interested in integer values of x that start from 1, and which means that for those values of x, our fitting function is actually decreasing. So, and we don't really care about what happens when x is 1/2 or something like that. It doesn't matter, right? So which means that the sequence is decreasing and our series converges, right? And basically this is the same um, solution, only typed nicely. And again, so the conclusion of the alternating series test is always that the series converges. So if the series diverges, then it means that we cannot apply the alternating series test.